Nothing within the simulation can be used to prove the simulation. This concept is not just a philosophical quandary but resonates deeply with Gödel's incompleteness theorem, a cornerstone of mathematical logic. Gödel's theorem reveals that in any sufficiently complex and coherent formal system, such as one capable of expressing basic arithmetic, there are true statements that cannot be proven within the system itself. Furthermore, a system cannot prove its own consistency without stepping outside its own framework. Applied to the idea of a simulation, this insight suggests that if our reality is a simulated construct, any attempt to prove the simulation's existence using tools, observations, or logic derived within the simulation will inevitably fall short. All elements within the simulation, our physical laws, mathematical systems, and even our perceptions, are conditioned by the simulation's underlying code or architecture. This inherently limits our capacity to transcend the system and gain an objective vantage point to confirm its nature. This limitation raises a profound question. If we cannot prove the simulation from within, are we forever bound to uncertainty? Gödel's theorem does not merely highlight limits. It also opens doors to meta-reflection, the exploration of what lies beyond the boundaries of a system. Similarly, we as conscious beings can adopt a meta-perspective to investigate the simulation hypothesis, not by seeking direct proof, but by examining its edges and potential inconsistencies. For instance, certain phenomena within our reality appear to defy conventional understanding or hint at a deeper structure underlying the observable. Consider the non-local behavior of particles in quantum mechanics, where entangled particles influence each other instantaneously, defying classical notions of space and time. Such behaviors may point to underlying mechanisms or architectures that transcend the apparent limits of the simulation. Similarly, consciousness itself, its origin, nature, and subjective experience, resists reduction to physical processes, suggesting it could interface with or even originate outside the simulation. Additionally, synchronicities, those meaningful coincidences that seem to defy probability, might reflect subtle disruptions or intentional signals from a deeper reality interacting with the simulated framework. These anomalies function as cracks in the simulation's facade, offering tantalizing glimpses of something beyond. If we accept the idea that our reality operates like a program, these irregularities could represent the limits of the simulation's coding or intentional artifacts introduced by the system's creators. They might even serve as the simulation's equivalent of breadcrumbs, encouraging us to question and explore further. While absolute proof of a simulation may remain inaccessible from within, this doesn't render the investigation futile. Instead, it inspires a shift in perspective. Rather than seeking conclusive evidence, we can map the rules, inconsistencies, and boundaries of our reality. By identifying patterns and exploring their implications, we engage in a process of reverse engineering the simulation. This speculative inquiry doesn't lead to certainty but expands our understanding of the structures and principles that shape our experience. Ultimately, this approach echoes Gödel's theorem, reminding us that systems are inherently limited in their ability to define themselves. However, these limitations also point to the possibility of transcending the framework, not by disproving it, but by engaging with its edges, anomalies, and potential connections to a more fundamental reality. Whether or not we are in a simulation, this process of inquiry deepens our understanding of existence and invites us to explore the boundaries of what we know and what we are capable of knowing.